So one of the theorems I've heard in Euclidean geometry, actually is a theorem or is it a postulate, whatever, that given a straight line, every straight line can be bisected.
Okay.
That means this side of it equals to this side of it.
It is possible to divide into two
equal
exactly
parts.
equal or congruent pieces.
Yeah. So A, B, C.
Yeah.
AB equals BC.
So let me write that down. So what's the
conjecture?
Conjecture. Okay. So the conjecture is every finite line, sometimes people call this line segment.
Let's say straight line.
Yeah, every finite straight line. Straight line can be
Bisect.
bisected, meaning
Let's use the word bisected.
bisected, which means divided
Into two equal.
into two equal halves. Okay, that sounds eminently reasonable.
Yeah.
But the question is, how do you prove that?
Yeah. So let's leave that in this in over here. What I want to do is move from the geometry which we study in school, Euclidean geometry, and move to another type of geometry called discrete geometry.
Okay. So you're going to assume that this is true.
Yeah. Let's not spend time on that. We can look. People can look that up. On
Yeah.
Google.
Okay.
Let's move to discrete geometry.
Mm-hmm.
In discrete geometry, what happens is that the paths from here to here it doesn't have infinite points. It has a finite set of points. So path from A, so say you have A here and you have B here. There would be some various different types of discrete geometry, but one type of discrete geometry will have finite points.
Finite number of points. Okay. So let me before we go on to that.
Yeah.
Let me write that down in Euclid. Euclidean geometry.
Yeah.
Every finite line, whether curved or straight, doesn't matter. Every finite line has infinitely many points.
In fact, for Euclidean geometry, you need to state even more than that about limit points and stuff, but let's leave that aside.
Yeah. How many? So if you have a line, for example, extremely short, if I ask you how many points does it have?
You would say an infinite.
Yeah, right. So you cannot keep on counting; it never ends.
Yeah.
Okay. Whereas here you are proposing a geometry, a discrete geometry, which is not Euclidean.
Non-Euclidean and non-continuous.
Non-continuous, discrete. Yeah. Every finite line has a finite number of points. So that means if there's a line this long and if there's a line this long, this will have more points than this one.
Yeah.
Okay. So a line can have 20 points.
Assuming the points are equal distances apart.
Yeah. Right.
I think that is.
So supposing I said the length of a line is the number of points it has.
Yeah. So length of line now becomes number of points.
So if a line has 21 points, another line has 20 points.
Yeah.
21 is longer.
Longer.
Okay, fine.
So let's take a line with. Let's see if this theorem, every finite straight line can be bisected.
Yeah.
So let's. So let's say a line with 6 points.
6 points, okay.
So that can be bisected, right? You can break it up here, and you'll have these 3 points as part of one line, and these 3 points as part of another line.
what does bisect mean? Does it mean, for example, one notion of bisect is intersect with another line? Is that what you mean, or is that something else?
Here we are using this definition of bisect divided into two equal halves.
Okay.
You can use the other one also and we'll get a different answer.
Different answer, okay.
Yeah. So if you're saying it has to intersect on other points and everything on one side has to be equal to the other, then here there's no way to break this up into two equal halves.
Right.
Right? But now if you have 5 points, by that definition of bisect you can't break it into two equal halves. Right? By this one, divided into two equal halves.
Okay. So if you divide into two equal halves, if there are 6 points, you will do it here.
Yeah.
You will do it here, and 3 here and 3 here.
3 here and 3 here. If you have 5 points, now you can't. They can't go through a point.
One of them will have 3 and
one of them will have 2. Yeah. However, now if your definition requires a line to intersect, and this part are the 2 lines. In that case, if this now has
drawing it through a point.
And this now has equal on each side. And this, now with 6 points, it's impossible.
Right. Because one will have
3 and the other will have 2.
Yeah. So whatever your definition of bisect, you will find
there will exist some
lines which are not
bisectable. But different lines are not bisectable given a different definition. This is the important part to look at definitions when we in the world, because how you define something completely changes the consequences.
So what that means is that whether the statement is true, every finite line segment can be bisected. Whether it is true or not depends upon
where we are living, which world
we are living. Euclidean world, where this is true, or the non-Euclidean world, where every finite line has finite number of points. So it depends upon the axioms and the definitions. Truth will depend upon those.
Okay.
Okay.
So let's